Engineering Large Software Systems, Week 3, The Role of Process. This week we move from the problems into characterizing the environment of engineering large systems. In particular, we're going to spend the next 3 weeks discussing process. Not so much what is in the process, that comes later. Rather, we'll discuss how to deal with process and process improvement as part of the engineering activity. This week we look at how process changes as systems get bigger. We review process and process improvement from a historical point of view, and then we'll look at some of the key ideas and approaches. In our discussions of the past weeks, one of the continuing themes has been that software, being invisible, is generally managed through engineering processes. This is not to imply that software development can be handled like manufacturing. It can't. It's development. The process used must fit the activities and needs of that development. It is most important in organizing, coordinating, and making visible development progress. As we said last week, large systems just exacerbate Brooks' werewolves. Complexity generally follows size. Conformity reaches farther and wider as the project grows larger, particularly when you consider legacy and supply chain issues. Changes are just as easy to make, but have much more subtle and far-reaching effects. And in general, the visibility into what is being accomplished is lower and can get downright murky. The benefits of having good, improving processes is that the process architecture, that is, the structure and relationships of the processes used in a development, can provide a central organizational construct for the project activity. It can increase coordination and visibility, speed up negotiation and decision-making, and offer a common language across multiple teams and groups that are often distributed and whose memberships evolve over time. In fact, on most large software development projects, the process is specific and evolving, just like the product itself. If it isn't, the project is probably doomed. Of course, for every benefit there is usually an associated risk. If we focus too much on process, we may respond to every issue by adding more process, or we may forget that the development is really about the customer, not the process. If analysis paralysis is a problem in other places, so process procrastination, where we spend so much time obsessing over how we do things that nothing ever gets done, is just as bad. Process also exacerbates the tragedy of the commons. Too rigid a process allows practitioners to ignore the common good when activities are not specified in their process. This generally falls out in support activities that are not directly related to construction. If we are careful in how we create and instantiate process, we can determine the right amount of ceremony for the context, that is, the schedule, budget, risk profile, and so on of our project, and then we can mitigate most of these risks. Although you may have discussed process in detail in other classes, I think it's important to remember where the processes we use and the idea of process improvement came into being. This is particularly important given the interpretation of some process improvement guidance without really understanding its genesis. So let's review some of the major players and their contributions. Process improvement in the Western world started, surprisingly, with a figure of note. Benjamin Franklin, in his Poor Richard's Almanac and his The Way of Wealth, highlighted the need to control inventory and waste. He could be said, even with his sturdy figure, to have been the first lean proponent. At the end of the 19th century, Frederick Taylor began our more modern process improvement. Peter Drucker, back in 1979, said, "Taylor was the first man in recorded history who deemed work deserving of systematic observation and study. On Taylor's scientific management rests, above all, the tremendous surge of affluence in the last 75 years, which has lifted the working masses in the developed countries well above any level recorded before. Taylor, though the Isaac Newton, or perhaps the Archimedes, of the science of work, laid only first foundations, however. Not much has been added to them since, even though he's been dead all of 60 years. Taylor's approach of scientific management consisted of 4 principles. replace rule-of-thumb work methods with methods based on a scientific study of the tasks, scientifically select, train, and develop each employee rather than passively leaving them to train themselves, provide detailed instructions and supervision of each worker in the performance of that worker's discrete task, and divide work nearly equally between managers and workers so that the managers apply scientific management principles to planning the work and the workers actually perform the tasks. One thing to remember as we continue along the process improvement story is that Taylor was looking at industrial factories and an uneducated workforce, a workforce that he seemed to hold little regard for. He once told a congressional committee that, "I can say without the slightest hesitation that the science of handling pig iron is so great that the man who is physically able to handle pig iron and is sufficiently phlegmatic and stupid to choose this for his occupation is rarely able to comprehend the science of handling pig iron." The next chapter of the story revolves around Walter Shewhart, a physicist, engineer, and statistician with Western Electric and Bell Labs. His two primary innovations that are with us still, for good or bad, are statistical process control and the plan, do, check, act cycle. Statistical process control, or SPC, is a way of managing the variance of a process using probabilistic techniques. It identifies problems as measurements that fall outside of a statistical limit that's based on historical and current observations. It defines the events that fall outside of these limits as due to one of two causes. First, there is an assignable or common cause, and that's within the activities of the process and can therefore be eliminated. Otherwise, the cause is a chance or special cause, one that is unanticipated, emergent, or otherwise outside of the process. Reducing or eliminating common cause events makes the process increasingly statistically predictable, excepting special cause events. SPC is a key component of high maturity as defined by the capability maturity models. Shewhart's second contribution is really a simplification of the first. Deming popularized the idea that the plan, do, check, act cycle was a basis for improving any kind of process, and so it's called the Shewhart cycle. It's defined as plan, establish the objectives and processes necessary to deliver results in accordance with the expected output, do, implement the processes, check, measure the new processes and compare the results against the expected result to ascertain any difference, act, analyze the differences to determine their cause. Each will be part of either one or more of the PDCA steps, and so you'll continue to do PDCA until you have a plan for improving your process. Now we move from the process improvement and management field to the field of quality. Joseph M. Juran actually worked in the Western Electric Hawthorne plant that was the pilot of Shewhart's SPC experiments. This began his career, which involved not only becoming the foremost proponent of quality management, but also rediscovering the work of Vilfredo Pareto, author of the famous 80-20 rule. Juran was primarily known for bringing the human element into the scientific management field. He drew inspiration from Margaret Mead's landmark work in cultural anthropology to develop his concept of business quality. He put these ideas into practice in Japan after World War II, where he helped change the world's perception of the term made in Japan. From Japan, he brought back ideas such as quality circles and cross-functional management. He founded the Juran Institute, which is still a leader in quality and process study. At about the same time as Juran, our next process master was also working in Japan. W. Edwards Deming used many of the same ideas and techniques, but emphasized statistical process control. His work was summarized by one of his followers as this: Deming taught that by adopting appropriate principles of management, organizations can increase quality and simultaneously reduce costs by reducing waste, rework, staff attrition, and litigation while increasing customer loyalty. The key is to practice continual improvement and think of manufacturing as a system, not as bits and pieces. Deming's reputation grew when in 1981 he was brought in as a consultant by the Ford Motor Company. Following his advice, within 5 years, Ford had become the most profitable American automobile manufacturer. Juran and Deming's work led directly to the quality movement and approaches like total quality management and Six Sigma. Phil Crosby is known for the statement, "Quality is free." A businessman and quality manager for the Pershing missile, he developed doing it right the first time as a response to America's loss of market share to Japan due to quality. He outlined a 14-step program based on 4 major principles. The definition of quality is conformance to requirements. The system of quality is prevention. The performance standard is 0 defects. The measurement of quality is the price of nonconformance. The last key figure in our list is Taiichi Ohno, the father of the Toyota production system. The TPS was the basis for lean manufacturing and all the subsequent lean approaches. Lean improvement is focused on eliminating waste from the process, and we'll talk about that much more later in the course. Now I know that you're all thinking, hey, these guys all were discussing manufacturing. And you would be right. However, much of what we think of as software process improvement is directly related to these manufacturing concepts. Plan, Do, Check, Act is the basis for nearly every process improvement approach. The 5 levels of a capability maturity model are based on 5 levels of quality from Crosby's Quality is Free. Statistical process control is used and misused by most large software producers. But the idea that software development is like manufacturing is both prevalent and dangerous. We will see its effects as we discuss process in later classes. Let's look at some examples of process improvement methods and tools. We've already talked about Plan, Do, Check, Act. It is the basic engine for several others, including the SEI's Ideal model and the Garcia-Turner decision-based life cycle for improvement. The basics of DLI are in your textbook and really just extend the Schuhart cycle with agile concepts and a try-before-you-buy attitude. One can consider Lean and Six Sigma as approaches or as frameworks. One of the most interesting and rarely implemented approaches came out of the University of Maryland and the Fraunhofer Center for Empirical Software Engineering. Vic Basili and Dieter Rombach started with their goal question metric process, added the concept of empirical methods and business goals that had been proven at NASA's Software Engineering Lab for over 25 years, and created the Quality Improvement Paradigm. It is unique because it isn't based on a specific process framework. Now, there are many such frameworks, including capability maturity models. The current CMM is CMMI. There are also ISO standards like 15288 and 9000. There's ITIL, which is the Information Technology Infrastructure Library, and also COBIT, Control Objectives for Information and Related Technology. Now, all of these are available, and also they're described in your text. Regardless of the approach or framework, there are some fundamental ideas that can make the difference between successful PI projects and disasters. We have said that development was a learning process. The same is true for process improvement. Process improvement needs to balance the internal focus with the external results. If your improvement doesn't impact customer satisfaction, it will have a hard time affecting the bottom line. Another way to say this is that PI should be driven by business goals. PI also has to improve the agility of the organization and not add barriers. It can't become rigid and sacrosanct. Let's face it, change-averse change agents aren't very successful. Above all, process improvement must be intentional, continuous, and integrated. Intentional because it won't happen on its own or without sponsorship. It must be approached and managed just as a project and not seen as other duties as assigned. Continuous because change is inevitable and processes need to react and evolve just like products. Integrated because if it is attempted in a vacuum or competing with one or more other improvement initiatives like TQM or business reengineering, it will end up as a turf war between the proponents. And as Abe Lincoln said, a house divided cannot stand. Process work is hard, but the results can make the difference between success and failure. This ends our introduction to process and its role in large systems. Next week, we'll look closely at a specific process framework. its strengths and its weaknesses.